So welcome and thank you for following the teachings. I request you kindly share this broadcast with your friends. Tell them to subscribe, to share. Make sure it reaches every student you know. So thank you very much. I would like to continue with the topic quantity of heat, whereby we've discussed it and so far so good. We now continue with the change of state, because we say that matter can change from one state to another due to temperature differences. In the former lesson, I had introduced something called latent heat of fusion. The heat energy absorbed as a solid turns into a liquid at the point called melting point. At that point, temperature remains constant until all the solid into a liquid, then temperature increases again. And we discussed the method of mixtures. So in this case, I would like us to see now determination of latent heat of fusion, but now using the electrical method. Therefore, to use the electrical method in determining the specific latent heat of fusion, this is what we do. We arrange the apparatus first of all as shown. So let me assemble the apparatus, then we'll be discussing now the procedure thereafter. So arrange for the electrical method. For the electrical method, arrange the apparatus as shown. Arrange the apparatus as shown. So the shown is here. There's a circuit for source of power here. We have a rheostat here to control the current flow. Then we got now this other hand. An ammeter connected here. Then we proceed to get the so we want to see how we can determine the latent heat of fusion of ice using the electrical method when ice has been melted using electricity. Therefore, we have a funnel here which is filled with ice. These are ice particles. An electric heater has been dipped or immersed completely inside the ice. So now you collect the ice which will melt here in another beaker. So you collect now the ice which will melt here. Collect water here. This is water. That is water. Then this is a thermometer. Keeping a thermometer here. It's a thermometer. That's the thermometer. We have ice here. So we want to check the, after connecting the we want to check the water which will melt here, and that will be the ice which has been turned into liquid water. At the same point, you'll set up another experiment B here. I will its purpose with an equal mass. And you also collect water. So this is the P and this is Q. Funnel P and funnel Q. Q is just naturally being left outside, nothing is happening. Like that, then you collect some water also there. So that's how you set up the apparatus with P connected to an electric source. So we have it melting some ice to water, and the key also melting some ice to water there. Therefore, what happens here? Switch on the heater. Switch on the heater. Switch on the heater. As you start timing, switch on the heater. Switch on the heater as you start timing. As you start timing, and place an empty beaker. An empty beaker below funnels P and Q. So in each case, have a beaker below them to collect the melted ice into water, like that. Then again, the beaker should be of non-mass. The beakers should be of non-mass. Yeah, that's basic. Non-mass. Not the reading of diameter, not diameter, and voltmeter readings. Not diameter and voltmeter readings. Then, when a reasonable amount of water has been collected under P, when a reasonable amount of water has been collected in P, the beaker at P, stop the current and record the time. Record the time. You can measure the mass of the water in P and in Q. Measure the water which has been collected in each in each case. Measure the mass independently. So after that, this is how you will now assemble the results. What we want. We said ice turns into water without change in temperature, and therefore the amount of heat energy which is needed by ice to change into liquid water is multiplied by, is given by mass times the latent heat of vaporization or latent heat of fusion of ice or of water, because there is no change in temperature. So it's mass times latent heat of fusion. Therefore, we are saying that now the results now mass obtained in P and mass in Q be M2. Let the masses be that way, M1 and M2. M1 and M2. So with M1 and M2, we can note this. Q is a control experiment to give us the mass of water which is melted due to the heat in the environment. Due to the heat in the environment. This is what we mean, because in P, this funnel is open. Therefore, that warmth will still cause some melting on the ice. That's why we have another funnel here with an equal mass. So that when now some water has melted out due to the natural heat in the atmosphere, then we collect the mass here of the water, and now the mass which has collected in P, it is not totally due to the electricity. There is one which is not natural, and that's why we have this experiment, so that now we may say mass of water purely melted by the electricity will be mass 1 minus mass 2. The mass which will be obtained here minus the mass which will be obtained here, because naturally the mass which is here could still have been melted here without the electricity. That's why to get the mass due to the electric current, now we go to subtract the two masses. Therefore now, mass or the heat energy supplied by heater is equal to heat energy melting, heat energy which is melting the ice. Therefore, heat energy supplied by heater, because we measured the voltage and the current which is power, and we recorded the time of the experiment, then will be equal to heat energy for melting the ice. Because there is no change in temperature, it will be mass, which is M1 minus M2 times the specific latent heat of fusion of ice. So of fission, latent heat of fission of ice. Therefore, to get latent heat of fission of ice, IT, all divided by the mass, and the SI unit will be joules per kilogram. Joules per kilogram. So that's the experiment. So generally we can now define what specific latent heat of fission is. Specific latent heat of fission is the amount of heat energy to change a unit mass of a substance from solid to liquid without change in temperature. Temperature at constant temperature. That heat energy absorbed by a matter, by a substance, so that it may change totally from a liquid to a solid to a liquid. We say that an equivalent energy is released as the same liquid loses heat to a solid. So that's what happens. We can check it latent heat of vaporization now. Latent heat of vaporization. Latent heat of vaporization. And we say that now, when you are heating a liquid, heating curve, and say of water. So when you start heating water, it increases the temperature until it's 100. And at 100 degrees Celsius, which is the boiling point of water, the water boils until all the water changes to vapor. And now after changing to vapor, now the temperature of vapor can continue increasing. Now, temperature is constant, there is some heat being supplied to, and that heat does not increase the temperature of water. It is strictly being used to break the forces of molecules attracting water molecules together. And now when they break, the water melts. The water vaporizes. Yeah, it vaporizes or evaporates to a gas. Now during the evaporation, okay, it boils as it evaporates to a gas. And at that point when it is boiling, the temperature remains constant. So that heat which is applied until all the water has vaporized, we call it the latent heat of vaporization. Latent heat of vaporization, we can mention it, latent heat of vaporization, which is the amount of heat to change a unit or to change a given mass of a substance from liquid to a gas at constant temperature. Therefore now we have the word specific. Heat of vaporization, which is the quantity of heat or the amount of heat energy required to change of a substance from liquid to gas at a constant temperature. Therefore, as the liquid changes to a gas, temperature remains constant. And we're saying again, NB, when the gas is losing heat energy to become a liquid, a similar amount or the same amount of energy is released. At that point when the gas will be condensing back to a liquid, a similar amount of heat energy gets released. So you can check an experiment now to determine the specific latent heat of vaporization of a substance. Let me get a duster. This side. So in the experiment now, to check the heat energy which is released as a gas condenses back to a liquid can be determined using the experiment below, determining the specific latent heat. Specific latent heat of vaporization. Specific latent heat of vaporization of ice, of water, sorry, or of vapor. As water vapor comes back to water, what amount of heat energy is released? We can check the experiment to determine that. You can arrange the apparatus as shown. You have a setup here where we got a stand here. So we look at the experiment, we assemble the data, we see how the latent heat of vaporization is determined. After that we see an example, at least one. So we have a flask here containing water. This one is dipped here. Then we have now this delivery tube, which will now bring steam generated into a well-lugged copper calorimeter. So we have a calorimeter here now, which has a stirrer. We have a stirrer DT. It is well lapped. It's coated with a material which is a poor conductor or an insulator. And we have the calorimeter now, like that. So calorimeter is having some water. So now you are supplying steam to the water now. Supplying steam to the water. So what you do is record the initial temperature of water in the calorimeter. So this is the water. This is a calorimeter. This one is a delivery tube. We have a thermometer here. Thermometer dipped here. Thermometer is there. This is a beaker with the water. And it's being heated. That's heat. So this is water. So when heated, rated, this is a stand, this is a flask. So what you do here is record the initial temperature of water in the calorimeter. Record the initial temperature of water in the calorimeter. Can have it as liter 1. Then after that, you boil the water until steam starts issuing out. Boil the water in the flask until steam starts issuing out through the tube. Then now once it starts, water starts coming out now, you now fix. Then you fix the tube now, the delivery tube in the calorimeter. containing water and stir. So you are directing the steam into the calorimeter, and you are stirring. You are stirring now. After some time, withdraw the tube, measure the mass of the calorimeter and its content. Can have it as mass too. And also the new temperature. The new temperature can be liter 2. The new temperature can be liter 2. So basically what is happening here, steam is getting generated here. It's directed into the calorimeter, which is having some water. Therefore, the steam now has to lose energy. Remember, it's at 100 boiling water. Steam is generated at 100. Therefore, it gains water. It first of all becomes water at 100. Then again, it loses the energy of the boiling water now. Because immediately after condensing into a liquid, it's at 100. So it starts losing temperature until it arrives at a common temperature with the water and the calorimeter. Now we measure that steady temperature. Therefore, we can say now, we can assemble the results now. The results. So we can say we have a mass of calorimeter as M1 and mass of calorimeter and water as M2. So mass of water now will be M2 minus M1. Now mass of calorimeter and the content after experiment will be mass 3. So mass of condensed steam, the steam which will have changed to water will be now the mass 3. The mass 3, which is calorimeter and content, minus mass 2. When the calorimeter adjusts water, we'll get now the steam which has condensed into water inside the calorimeter. Therefore, now we can say heat lost by condensing ice, which happened at a specific constant temperature, plus heat lost water from 100 boiling point up to the common point temperature 2 achieved, will be equal to mass absorbed by calorimeter plus mass absorbed by water, the water which was initially in the calorimeter. Therefore, what's happening here, there is mass of the condensing ice, and you have said the condensed ice will have this mass 3 minus M1 times latent heat of vaporization. So this is happening at a constant temperature, so there is no change in temperature here. Plus now, once it has become water now, it now starts losing its energy as water, the same mass times specific heat capacity now of water, which is known, times change in temperature from 100 until theta 2, which is the common temperature there. It will be the same as mass absorbed by the calorimeter, which will be mass of calorimeter was m1 times specific heat capacity of the calorimeter times change in temperature. They were initially at 1 and they are raising to 2. So theta 2 minus theta 1 plus mass gained by water. There was water inside the calorimeter, therefore mass of the water, and we have said the mass of the water will be determined by now m2 minus m1 times specific heat capacity of water times change in temperature from theta 1 to theta 2. So it will be this one. And in this expression, the only unknown is the latent heat of vaporization of ice, or of steam, steam to change back to water. Latent heat of vaporization of steam. So we can take an example to understand the concept better. Let me give an example. So we can take an example for this. By I'll write the example, then we systematically. Dry steam is passed. Dry steam is passed into a well-lagged calorimeter of mass 0.25 kilograms, containing 0.0 kilograms of water and 0.02 kilograms of ice at 0 degrees Celsius. The mixture is well stirred. The mixture is well stirred and cut off steam supply cut off when the temperature of the calorimeter and its content, when the temperature of calorimeter and condense, or the common temperature in other words, is 25 degrees Celsius. Neglecting heat losses, find the specific latent heat of vaporization. Find the specific latent heat of vaporization of water if 25 grams of steam is found to condense to water. Is found to have condensed to water. Then latent heat of fusion of water. Latent heat of fusion of water is given as 3.36 times 10 raised to 5 joules per kilogram. So now let me take you through the question slowly. We are saying that there is steam. Now steam is coming into a calorimeter and this calorimeter is already adding water. It's adding water and it's adding ice. Ice and water. So ice and water, they are at 0 degrees Celsius. Then we have steam which is coming. It will be condensed first of all, and after condensed, it again loses, because it will be condensed to water, and at that time of condensation they will be at 100 degrees Celsius. Therefore, it will lose again temperature until it comes to 25, which is the common temperature. As the dry steam gets condensed, and the condensed steam, which is now water, loses energy up to 25, there is now ice inside the calorimeter with the water and the calorimeter in itself, which are gaining the heat being lost by the condensing steam and the cooling water. Therefore, now we can say heat lost by condensing steam plus heat lost by water. Steam has condensed to water now. The water loses, because it's 100, it loses heat energy until it becomes 25 degrees Celsius. Now, as it loses energy now, this will be the same as heat gained by calorimeter plus heat gained by water plus heat gained by the ice, which add to melt. Therefore, here, heat lost by steam, we have 25 grams of steam which have condensed. So 25 and divide by 1000 to get SI units, which kilogram, times the latent heat of fusion, because it absorbed heat of fusion at that point, plus heat lost by water now. So the water is having this mass times specific heat capacity times change in temperature. It is at 100 after condensing to water, so it dropped up to 25, meaning 75 is the change in temperature. It will be equal to heat gained by calorimeter, a copper calorimeter, and the specific heat capacity of copper is 4. We'll have the mass of the calorimeter of 0.25 kilograms. 0.25 times 400 times change in temperature. They were at 0. Calorimeter and the ice and the water, they were at 0, and they have gone to 25, meaning the change is 25 plus heat gained by water. Now, let's deal with ice first. For ice to melt, it is the ice which was there containing 0.02 kilograms of ice. Therefore, it's 0.02 kilograms of ice times the latent heat of fusion. So that ice might melt. Latent heat of fusion, so that ice might melt. So 3.36 times 10 power 5. So that ice has melted. Plus now, heat gained by water. So after it has melted, it becomes water. Therefore, the 0.02 of ice has become water, and initially there is still some water. There is still some water. 0.5 kilograms of water. Now this times the specific heat capacity of water, 4200, times the change in temperature from 0 to 25, we got 25. So that is the comparison which is happening here. Now we can multiply this. We get 0.025 latent heat of vaporization, 0.025 plus this case multiplied, we'll have 25 by 25 times 4200 times 75, then we divide over by 1000, we get 7875. It will be equal to this side multiplied, we'll have 0.25 by 400 by 25, this is giving us 25, plus 0.002 0.02, not two zeros, 0.02, yeah, 0.02 kilograms times 3.36 times 100,000, like that. We get 6720 plus 0.02 plus the water, which was initially there 0.5, we get 0.52. So we multiply it by 4200, the specific heat capacity of water, by changing temperature 25, and we get 54,600. These are all energies in joules. Energy in joules. Therefore, we can add up 2500 plus 6720 plus 54,600. This gives us 63,820. Then we subtract this one, 7875, and we get 55,945, which is equal to 0.25. The latent heat of vaporization of ice, latent heat of vaporization of water, which will be, when you divide this, we get 2,237,800 joules per kilogram, which can also be written as 2.2378 times 10 raised to power 1, 2, 3, 4, 5, 6 joules. In standard form, it can be expressed this way. So this is the latent heat of vaporization of water, which is required so that steam at 100 degrees Celsius can change water, which is still at 100 degrees Celsius, changing of state without change in the state of, without change in temperature, because it being lost is used to bring the particles of water together and not to decrease the temperature. Therefore, without decrease in temperature, it is lost. So that vapor become and condense to a liquid, and that is the heat which was required for this process. So thank you very much for listening. I can commission students to follow up with more examples on this, so that as we meet, then you'll be good and able to continue understanding as we pursue deeper concepts in the same topic. So thank you very much for following. I can wish you a nice stay.